Uranium is one of the most powerful and controversial materials ever extracted from the Earth, capable of producing enormous amounts of energy from incredibly small quantities of fuel. Yet its journey from buried rock to electricity powering entire cities is a process few people ever see or fully understand. What begins as trace amounts of radioactive metal locked deep underground must pass through mining, chemical processing, enrichment, fuel fabrication, and tightly controlled reactor systems before it ever generates usable power. Behind every nuclear power plant lies a vast industrial chain governed by physics, geology, chemistry, and some of the strictest safety regulations on the planet. And today on The How Factory, we're taking a deep look at how uranium is mined, processed, and used to power the modern world. The story of uranium begins long before nuclear power existed. Uranium was identified as a distinct element in the late 18th century, but for decades it was used mainly for coloring glass and ceramics. It wasn't until the early 20th century that scientists discovered uranium's ability to release enormous energy through nuclear fission. This discovery reshaped global energy, science, and geopolitics. After World War II, attention turned from weapons to electricity, and nuclear power emerged as a way to produce massive amounts of energy without burning fossil fuels. Today, uranium fuels nuclear reactors that provide reliable baseload power to millions of homes across dozens of countries. Modern uranium production begins with geology. Uranium is not found in large metal chunks but dispersed in rock at very low concentrations. Even high-grade uranium ore often contains less than 1% uranium by weight. Geologists use airborne surveys, ground sampling, and radiation detection to locate economically viable deposits. Once a deposit is confirmed, mining methods are chosen based on depth, ore concentration, and surrounding geology. There are three main uranium mining methods. Open-pit mining is used when deposits are near the surface. Large excavators remove overburden to access ore-bearing rock, which is drilled, blasted, and hauled to processing facilities. Underground mining is used for deeper deposits where tunnels and shafts are constructed to access ore bodies. Both methods resemble conventional metal mining, but operate under strict radiation controls. The third method, increasingly common, is in-situ recovery, or ISR mining. Instead of physically removing rock, operators inject a leaching solution into the ore-bearing groundwater. This solution dissolves uranium in place, and the uranium-rich liquid is pumped back to the surface. ISR mining minimizes surface disturbance and reduces waste rock, but requires precise control of groundwater chemistry to prevent environmental contamination. Once uranium ore or solution is brought to the surface, it enters processing. For conventional mining, ore is crushed and ground into fine particles. This material is fed into leaching tanks where chemicals dissolve the uranium. The uranium-bearing solution is then separated from solid waste. The remaining solids, known as tailings, are carefully managed and stored in engineered containment systems designed to prevent radiation exposure and groundwater contamination. The dissolved uranium is recovered from solution using ion exchange or solvent extraction systems. These systems selectively capture uranium while leaving other materials behind. The uranium is then precipitated, dried, and packaged as a concentrated powder known as yellowcake. Despite its name, yellowcake can range from yellow to dark brown and is not radioactive enough to be used directly as fuel. Yellowcake represents a major milestone, but it is still far from usable in a reactor. At this stage, uranium is typically around 70 to 90% pure uranium oxide. Yellowcake is sealed in heavy containers and transported under strict regulations to conversion facilities. Conversion transforms yellowcake into a chemical form suitable for enrichment. At conversion plants, uranium oxide is processed into uranium hexafluoride, a compound that becomes gaseous at relatively low temperatures. This step is critical because enrichment requires uranium to be in gas form. Conversion involves multiple chemical reactions and operates in heavily shielded facilities with rigorous monitoring. Natural uranium contains mostly uranium-238, with only about 0.7% uranium-235. the isotope capable of sustaining nuclear fission in most reactors. Enrichment increases the concentration of uranium-235. This process does not create energy. It simply separates isotopes based on their slight mass difference. Modern enrichment uses gas centrifuges. Uranium hexafluoride gas is fed into rapidly spinning centrifuges that rotate at extreme speeds. The heavier uranium-238 moves outward, while the lighter uranium-235 concentrates closer to the center. By linking thousands of centrifuges and cascades, enrichment plants gradually raise the uranium-235 concentration to the level required for power generation, typically between 3 and 5%. Enrichment is one of the most tightly regulated stages in the entire nuclear fuel cycle because higher enrichment levels can be misused. International oversight, tracking systems, and inspections ensure enrichment remains within civilian limits. Once enriched, the uranium hexafluoride is ready for fuel fabrication. Fuel fabrication converts enriched uranium into solid fuel suitable for reactors. The uranium hexafluoride is first converted back into uranium dioxide powder. This powder is pressed into small ceramic pellets, each about the size of a fingertip. Despite their small size, each pellet contains an enormous amount of potential energy. The pellets are sintered in high-temperature furnaces, making them hard, dense, and stable. After inspection, pellets are stacked into long metal tubes made from zirconium alloys. These tubes form fuel rods, which are sealed and assembled into fuel bundles. A single reactor core may contain tens of thousands of pellets arranged with extreme precision. Fuel assemblies are transported to nuclear power plants under strict security and safety procedures. Once loaded into a reactor, the uranium fuel begins its final role: energy production. Inside a nuclear reactor, uranium-235 atoms undergo controlled fission. When a uranium-235 nucleus splits, it releases heat and additional neutrons. These neutrons trigger further fission reactions, creating a self-sustaining chain reaction. Control rods absorb excess neutrons, allowing operators to regulate reactor power precisely. The heat generated by fission does not directly produce electricity. Instead, it heats water to produce steam, which spins turbines connected to generators. This process is similar to fossil fuel power plants. The difference lies in how the heat is produced. Nuclear plants generate electricity without burning fuel, resulting in extremely low carbon emissions during operation. Fuel remains in a reactor for several years. Over time, uranium-235 is consumed, and fission byproducts accumulate, reducing efficiency. When fuel is no longer efficient, it is removed during scheduled outages. Used fuel is highly radioactive and generates heat, so it is placed in water-filled cooling pools that shield radiation and remove heat. After cooling, used fuel may be transferred to dry storage casks or reprocessed, depending on national policy. Reprocessing recovers usable materials for future fuel, while waste products are isolated for long-term storage. Managing used nuclear fuel is one of the most carefully controlled aspects of nuclear energy. Safety governs every stage of uranium's journey. From mining to reactors, radiation monitoring, containment systems, and regulatory oversight are constant. Uranium itself is not especially dangerous when handled properly, but its misuse or poor management can have serious consequences. That is why nuclear fuel cycles are among the most regulated industrial systems on Earth. What makes uranium remarkable is its energy density. A small amount of nuclear fuel can power a city for years. Compared to coal, oil, or gas, uranium requires far less material, transportation, and land to generate the same amount of energy. This efficiency is why many countries rely on nuclear power for stable, long-term electricity. From early scientific discoveries to modern centrifuge cascades and reactor cores, uranium's transformation reflects humanity's ability to harness fundamental forces of nature. It is not just a mining story or an energy story. It is a system that connects geology, chemistry, engineering, physics, and global governance. From buried ore deep underground to ceramic pellets inside reactor cores, from controlled fission to spinning turbines and glowing city lights, Uranium's journey is one of the most complex and powerful industrial processes ever created. And that is exactly how uranium is mined, processed, enriched, fabricated, and used, transforming ancient radioactive rock into a reliable source of electricity that powers the modern world. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the materials, machines, and systems that power civilization.